Welcome back, everyone, to what will be the finale of the video series for this course. And for this video, I want to take the view that we're sort of wrapping up the natural questions that I haven't answered yet as we've talked about cardinality and sizes of sets. So I've outlined the three questions here that I'm going to answer. So last video, we proved that z plus and z plus cross z plus have the same cardinality, or the same z plus and q plus. But we did so cleverly in a way that used Cantor-Bernstein and didn't actually write down a bijection between the two sets. And so, realizing that what we proved last time means there has to be a bijection between the two sets, you might ask whether actually it's possible to write down a reasonable-looking bijection between these two sets. And so the answer is yes, and I'll go ahead and show that to you today. The next question is, we've talked a lot about two sizes of infinity, Aleph 0 and Aleph C, and so it's a natural question to ask, hey, is there an even bigger set than that? Is there a biggest size of infinity? And a long time ago, way back in the first week of the course, I talked about the set of all sets briefly and how that ends up being problematic, and that's going to tie into this discussion as well. Finally, we've drawn our picture where I have finite sets followed by Aleph 0, and I've argued for you before there's nothing between finite sets and Aleph 0, but then I also have this gap between Aleph 0 and Aleph C, and so it's a very natural question to ask whether there's any sets in between. So I will talk about that as we sort of wrap up today. All right, so that's our plan. Let's get started with question 1. Let's talk about what a bijection between the positive integers and the positive integers cross the positive integers would look like. Now, I'll note I've already proven formally that these two sets have the same cardinality, so I'm going to allow myself to be a little bit looser here than I would in writing if I were calling this a proof. I'm just going to show you that this can be done, and I think you'll be convinced that this can be done in a pretty natural way. So remember what z plus cross z plus is. It's this sort of endless sea of dots that extends infinitely up and to the right. And what I'd like to do is convince you that there is a bijection from z plus to z plus cross z plus. Now, before we noted that there's a lot of obvious things that are not going to work. So, for example, I might start here and say, okay, this is where I'm going to send 1, this is where I'm going to send 2, this is where I'm going to send 3, 4, 5, 6... except if I do that and I just keep going, I miss all of the dots over here, so that's not going to work. But it turns out there's actually a not too terribly unnatural pattern that you can take. Namely, we can proceed down the diagonals. So I'm going to go down this diagonal, so that is to say I'm going to send 1 here. Then I'm going to go down this diagonal, so I will send 2 here and 3 here, so that diagonal. Then I'm going to go down this diagonal. So there's 4, 5, 6, 7, 8, 9, 10, and so on. And so this is only a slight variation of the fact that it didn't work if I counted by row, because the row is infinite, and it didn't work if I counted by column, because the column was infinite. But if instead I count by these diagonals, then actually I can cover everything. And again, just to clarify this picture, I'm describing where 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. map by just labeling the dot with the thing that maps to it. So 1 maps to that dot, which would be 1, 1. 2 maps to that dot, which would be 1, 2. 3 maps to 2, 1. 4 maps to 1, 3. 5 maps to 2, 2, and so on and so forth. It's a bit annoying to write down an algebraic expression for this, but that's certainly not necessary in order for you to prove this, as long as you can carefully describe in words what this bijection is. But it is possible if you're curious. If you want to visualize our bijection from z plus to q plus, we can actually use the same idea. To do that, I'm going to arrange all the rational numbers in a two-dimensional grid, and just like the grid before, I'm imagining that this keeps going infinitely in these directions, and of course every rational number will appear in this table. Now, the problem, and we talked about this a little bit last time, is that yes, every rational number shows up in this table, but in fact every rational number shows up in this table infinitely many times. Because, for example, this 2 over 2 is the same as 1 over 1. This 2 over 4 is the same as 1 over 2. So what I'm going to do is I'm going to cross out all the fractions that are not in lowest terms, which is going to make it so that every rational number shows up in this table exactly once. Now, here's a silly aside before we finish this. You might ask yourself, okay, I showed you a 4x4 part of this grid. What if I blew this up to a much, much larger version of the grid? What percentage of the numbers am I crossing out? So in other words, in this little picture, I crossed out 5 of 16. But if I, instead of going 1 through 4, if I want, say, 1 through 1,000,000 or 1 through 10 trillion or whatever, in the limit, what proportion of numbers am I crossing out? And it turns out that it's possible to give an exact formula for the proportion of numbers that you're crossing out. It just also happens that the answer is absurd. Namely, the answer works out to be 1 minus 6 over pi squared. And if you're curious, this is very close to 40%. That's not really relevant to our discussion, but it was so neat I felt it was worth mentioning. Back to our discussion, though, how am I going to write down a bijection from z plus to q plus? Well, I'm going to use the same trick we did here with the diagonals, where I'm going to count down these diagonals. So I'll start with z plus, I'll end in q plus, with an arrow here. So 1 is going to go to 1. 2 will go to a half. 3 will go to 2 over 1. 4 will go to 1 over 3. And now we have our first instance where I've had to cross something out because it's not in lowest terms. And so sort of the most interesting part of this versus the previous example is, what do I do with the numbers that have been crossed out? And the answer is, I just skip over them. So when I go to see where 5 maps, I count 1, 2, 3, 4, and I just don't even count this. So that's 5. So 5 maps to 3. Okay, and so then 6 will start up here at this next diagonal, which will be 1 over 4, and so on down the line. And just like we covered all the dots by going down the diagonals up here, similarly by doing these diagonals here, I'm going to cover all the rational numbers, and I'm just going to skip all the ones that aren't in lowest terms, and that will give me a precise bijection between the positive integers and the rational numbers. So that concludes what I wanted to say about question 1. Let's look at the second question again. So the second question is about whether there's a bigger set than a set of size Aleph C. In other words, is there a bigger set than the set of real numbers? And you might be tempted, just because this already has a name, to think, oh, well, the set of complex numbers is bigger than the set of real numbers. But in fact, no, and I'll leave this as something for you to convince yourself. The complex numbers, in fact, have a bijection with the real numbers. They are the same size. And so the complex numbers, in fact, also have size Aleph C. But there is a bigger set, namely, the set that's larger than the real numbers that's easiest to write down is the power set of the real numbers. In fact, I'm going to prove a much, much stronger result than that, also from Cantor. Namely, I'm going to prove that if I start with any set that I like, the size of the power set of that set is always strictly larger than the size of the set itself. So if you start with the integers, we showed last time that if you took the power set of the positive integers, that ended up having cardinality strictly larger than the integers. And just a moment ago, I said if you take the power set of the real numbers, that ends up having cardinality strictly larger than the cardinality of the real numbers. In fact, this is true no matter what set you pick. Now, we already kind of knew this for finite sets, because the size of the power set of a finite set ended up being 2 to that number, and so, for example, if you start with a set of size 10, then its power set has size 1024, which is certainly larger than 10. But, and this turns out to be a little harder to prove, but turns out to be sort of even more powerful, if I start even with an infinite set, if I take its power set, it only makes it larger. So my way of proving this is I'm going to show that no matter what function I start with, if it's a function from a set S to S's own power set, then that function is not onto. And if it's impossible for there to be an onto function from one set to another, that tells you that the first set has size strictly less than the second set, via our definitions of strictly less and Cantor-Bernstein and all of that good stuff. So that's what we're going to prove. We're going to prove it's impossible for any set to write down an onto function from S to the power set. Note, this isn't a proof by contradiction or anything. I'm not assuming that I have an onto function from S to its power set or anything like that. I'm just proving the positive statement that if f is a function from S to its power set, f is not onto. Now, the proof of this is very mind-bending and bizarre, just to warn you. So I'm going to define here a subset x of S. Namely, my subset x of S is going to be the set of x in S such that x is not an element of f of x. Now, remember, each x in S is getting mapped to a subset of S, and so that subset of S either contains x or doesn't contain x, so it makes sense to collect together all of those elements of S that map to something under this particular function that does not contain x. Now, how is this going to lead us into a proof that this function's not onto? Well, this thing is an element of the codomain, because it's a subset of S. So what are we going to prove? We're going to prove that even though x is an element of the codomain of f, x is definitely not in the image of f. So even though weird and mind-bending things are happening with this definition of this set x and trying to keep track of what a function from a set to its power set even looks like and all of these kinds of things, the overall structure of proving that this function is not onto is exactly the same structure we've used to prove that functions are not onto from the very beginning. Write down an element of the codomain, prove that element of the codomain's not in the image. And that's all we're doing here. It just so happens the element that Cantor helped us write down is weird. So, to figure out why this is never in the image, I want to consider the world where it actually is in the image. So that is, for sake of contradiction, I'm going to imagine that there's some element of the domain that does map to this set X that I have defined. So, for sake of contradiction, I'm going to imagine that there's some alpha in S, such that f of alpha actually is equal to X. Now, remember here, just so that we keep this straight, what's going on, I have X, a subset I have defined of S, and then I have alpha, that's a particular element of S, in the hypothetical universe where some element alpha maps to X. So, a natural question to ask might be, is this alpha in X? So, effectively here we have to consider two cases. What happens if alpha is in X? Well, if alpha is in X, what does that mean? Well, X is the set of elements of S such that that element is not an element of f of x. So if alpha is in X, then by the definition of X, that means alpha is not an element of f of alpha. All I've done here is say, okay, what are the things that are in X? By definition, it's the set of things where this is true. Well, thus, if alpha is in X, that tells me that alpha is not an f of alpha. But what did we assume? We assumed that f of alpha was X. So, Cliff Notes version, if alpha is in X, what we've just shown is that that means, by definition, alpha is not an X. So that's definitely a contradiction. If alpha is simultaneously in X and not in X, that's bad. So then it must be the case that actually alpha's not in X. And so if alpha's not in X, then Well, alpha is not in f of alpha, because remember, x is just f of alpha. If alpha is not in x, well, then that means alpha is not in f of alpha, and that's just because, remember, x is, by assumption, f of alpha. But now, alpha meets the definition of something that's in x. So if alpha isn't in x, then it is. And that's also a contradiction. And so just to summarize the structure here, we started with a function from S to its power set. We defined an element of the codomain, a particular element of the codomain, in terms of that function. Then we imagined that some element did actually map to that element of the codomain. That is, we imagined that this thing actually was in the image. So let's name a thing that maps to it. So I just went ahead and called that alpha. And so we had f of alpha here equaling x in this universe that we've dreamt up by supposing that actually x is in the image. But then we asked a very basic question about alpha, namely x is a set of things like alpha. Is alpha one of those things, or is it not? And we found ourselves in a very weird world, because if alpha was an x, that told us it wasn't. And if alpha wasn't an x, that told us it was. So actually both of these possible paths, that is, both cases, ended in failure. They ended in a contradiction that sort of broke the laws of logic. And so then the only way that that cannot break all of logic is if the assumption we made was wrong. Namely, the assumption we made that something did actually map to x. So in other words, when we imagined the world where something mapped to x, we were imagining a world that cannot exist. And so that means that in fact nothing maps to x, and so x is in the codomain but not the image. And those words exactly amount to saying that f is not onto. Now this proof is quite abstract and may be difficult to understand at first. So what I'm going to do is I'm going to go through everything that happened in this proof in the specific example of a function where the set involved is finite. So here, I'm going to take S to be the set of numbers 1 through 8, and then I'm going to pick a particular function from S to the power set of S. And if you're curious, where did this function come from? This is a function I literally had my computer generate at random. And the reason why I did that is because I want it to be very believable that this would work no matter what function was picked here. Because in order for this to constitute a proof that no function is onto, this always has to work. So here's our function written out input by input. And you can see that a function from S to its power set is going to end up being a rather complicated thing, because the power set has lots of elements. Now, in this particular instance, what is it we're going to end up proving? I'm going to prove that this function f is not onto. Now, if you're used to thinking about the pigeonhole principle by now, you might have noticed that this set has 8 elements, while the power set has 256 elements. And so there was really no hope, to begin with, that this function I would write down could ever possibly be onto. Indeed, as I noted before, the theorem we're proving that the power set is always strictly larger than the set itself, we already knew that for finite sets because we had a formula for the size of the power set. Rather, what I want you to get out of this example is the structure of the proof, namely how we constructed that weird set X that we ended up using inside the proof. Namely, what was X? X was the set of elements of S such that X itself was not an element of f of X. So to make this stand out as well as possible, I'm going to circle those things. So f of 1 is this set, which happens to contain literally everything but 1. So 1 is in X. By the same token, 2 is not in f of 2. So 2 is in X. 3, however, is in f of 3. And the thing I want you to see out of looking at this in such a concrete way is that asking whether x is an element of f of x or not is actually a pretty natural question, because again, f of some particular element is just a list of things that are like that element. In this case, 2 is like these numbers, it just happens not to be in the list, whereas 3 is in the list. Likewise, so is 4. But 5 is not in f of 5. 6 is in f of 6. 7 is not in f of 7. And 8 is not in f of 8. And so again, the way we define this, all the numbers that are in X are the numbers I've just circled in green. So that is to say, X is the set 1, 2, 5, 7, 8. This is exactly the kind of thing that this function maps to. In other words, this is in the codomain, but definitely not in the image. How do I know it's not in the image? Well, these are the 8 things that are in the image of f. And this is not one of them. So let's just check that. Okay, this one doesn't have 1, doesn't have 1. It's 1, 2, but has 3, whereas our set doesn't. This one doesn't have 1, 1, 2, but this one doesn't have 5. This one doesn't have 1 or 2. 1, 2, 5. F of 7 has 6, but our set doesn't, and f of 8 doesn't have 2. None of these sets are equal to X. And so what our proof has done is to very explicitly construct for us an element of the codomain that's not in the image, which seems like an impossible task given that you didn't know anything about the function to start with. But this proof lets us do this for any function from a set to its power set, regardless if that set is finite or infinite or what have you. Now, why does this work? Now, I gave this kind of abstract argument that this works by thinking about what happened in terms of elements of X. But this was actually done in a way that sort of assumed we were in a universe where this failed and actually somehow X accidentally was in the image. In this particular case, we have a very concrete function, and we have a very concrete set, and we can actually argue why it's not in the image in a pretty concrete way. Namely, I can just go number by number and see why X is not f of that number. So why is X not equal to f of 1? Well, the reason why X is not equal to f of 1 is that 1 is an element of X, but 1 is not an element of this set, right? No 1. Why is X not equal to f of 2? Well, 2 is an element of X, but it's not an element of f of 2. Why is X not f of 3? Well, because 3 is in f of 3, but it is not in X. And so actually, I can always see that f of a particular element is not equal to X by just looking at that element, because I have rigged it by my definition of X, so that X and f of that element always disagree on whether they contain that element. That is, of f of 4 and X, exactly one of them contains 4, so they can't be equal. Of X and f of 5, exactly one of them contains 5, so they can't be equal. And which one goes back and forth? So 5 is in X, 6 is in f of 6, 7 is in X, 8 is in X. And so actually, if you look closely at this proof, what we're doing here is almost identical to the proof we gave some days ago that you can't write down an onto function from the positive integers to the interval 0, 1. Just to remind you, that proof was here, where I supposed I had a function from the positive integers to the interval 0, 1. I wrote down all of the decimals of all of the numbers f of 1, f of 2, f of 3, f of 4, f of 5, and so on. And then I wrote down this weird number, and the way I made the number was to make it so that it disagreed in the first digit with the first one, in the second digit with the second one, in the third digit with the third one, in the fourth digit with the fourth one, and so on. That's exactly what's happening here in Cantor's other proof, where I've again made it so that this set X disagrees with f of 1 in whether 1 is in the set, disagrees with f of 2 in whether 2 is in the set, and so on down the line. And thus, once we accept this proof, what we come to realize is that in fact, every power set is larger than the set it is a power set of. Thus, if we wanted to extend our hierarchy to the right, all we'd have to do is say, okay, well, the power set of the real numbers is strictly larger, so it goes in some box over here. And then the power set of R, well, it goes in an even further box. And so in this fashion, I can keep making boxes that go on and on and on and on and on as far as I want. So there can be no largest set, because in fact I've given you a way, no matter how big a set is, to make a set that is strictly larger, namely, take its power set. So how does this connect back to the question I asked before about the set of all sets? And I'll tell you the punchline first, because the punchline is a bit counterintuitive. And the punchline is that the set of all sets doesn't exist. It's not a thing. And it feels like it's the sort of thing we should be able to make and work with. It feels like I know what's in it and what's not in it. But here is where our need for axioms comes in. The axioms don't allow us to make a set of all sets. And if we imagined for a moment that the axioms did allow us to make the set of all sets, something would go horribly wrong. And let me show you what it is that goes wrong if we imagine that there is a set of all sets. So I'm going to denote the set of all sets by this script S that looks kind of like a zeta, but I meant it to be a script S. So I'm going to imagine that this thing actually exists. And then I'm going to think about, and this is going to hurt a bit, so apologies in advance, I am going to think about the power set of it. That is to say, S is the set of all sets, and so the power set of S is the set of all sets of sets. Now, even though we've been talking about this for 2 minutes, and probably our brains already hurt, I claim there are 2 things that we can say with confidence about the power set of the set of all sets, if it exists. Thing 1 is I can say that the size of the power set of the set of all sets is strictly larger than the set of all sets. How do I know that? Well, we literally just proved that no matter what set you choose, the power set is always strictly larger. Now here's the worrying one. I also claim that the power set of the set of all sets is in fact a subset of the set of all sets. And note, this should immediately cause a bunch of red flags to go off. Because remember, the power set is supposed to be a vastly larger object than the set you started with. And yet here, the power set is actually a subset. Well, why is it a subset? It's a subset because the power set of the set of all sets is the set of all sets of sets. But in particular, everything in the set of all sets of sets is a set. And so if I imagine this set of all sets exists, well, then the set of all sets of sets is definitely a subset of it. But as soon as a set is a subset of another set, it shows you that the cardinality of that first set is less than or equal to the cardinality of the second set. Why is that? Well, there's a one-to-one function from a subset of a set to the set that just takes every element to itself. And so the existence of that one-to-one function then guarantees that in fact this set has less than or equal to cardinality of this set. But you don't have to look super far to see the problem, because on the one hand, it's obvious that the power set has strictly greater cardinality, and on the other hand, it's clear the power set has less cardinality, or at most equal cardinality. And these two things are in direct contradiction. And so because these two things are in direct contradiction, I can't allow a universe that has both of them. Which means I have to reject one of these two things. That is to say, either I reject the set of all sets, or I reject Cantor's proof that the power set of a set always has strictly greater cardinality than the set itself. Now, you may well be thinking, okay, great, I'll reject this one. And indeed, mathematicians at the time largely thought that Cantor's work made no sense, and assumed he must be missing something, and tried not to think too hard about it, and just figured this kind of thing just couldn't be true because it would obviously violate things that they took for granted, like the existence of the set of all sets. However, over the century or so since then, it has come to be understood that everything Cantor did more or less was correct. Cantor was the first person who really understood infinite sets and really understood all of these connections. And understood that, for example, this set of all sets just is not something that we can think about. Now, I'll note through all of this, I have kept referring back to the axioms. And I've done that as though we have ever discussed what the axioms of set theory are, or that it's something we've thought about. And throughout this course, I've in fact deliberately avoided talking about the axioms of set theory, or the axioms of the positive integers, or all of these kinds of things, because I want to believe that fundamentally positive integers and sets are intuitive enough objects that I don't need to write down axioms for us to start working with them. And so in a sense, when I do that, I'm implying that I believe the idea of a set is something that exists in the abstract, that a positive integer exists in the abstract, that it already exists, we already sort of understand it, and we're just studying its properties. However, this whole discussion throws a wrench into that idea, because we now have this whole fact that we sort of intuitively feel like there should be a set of all sets, but there isn't, at least not under quote-unquote the axioms. So does that mean the axioms are wrong? Can it possibly be the case that there's multiple sets of axioms that I could take for set theory? If there's multiple sets of axioms I could take, and they give me different answers, that almost makes it start to seem like rather than sets being an object innate to the universe that we're discovering, it makes it seem like it's an object that we're inventing when we write down the axioms. And that when someone else writes down axioms for sets, they're inventing a different object. And maybe the same thing is true for the positive integers. Who knows? This is actually a great way, if you want to get into very heated arguments on math Twitter, to discuss the question of whether math should be thought of fundamentally as something that's discovered. That is, are we thinking about and observing objects that in some sense exist, the positive integers, sets, groups, whatever? Or are we inventing each of these objects as we study them, as we write down the axioms? Are we as humans inventing them and they're not something that's sort of intrinsic to the universe or mathematical reality or whatever? I have no answer to this question, but I think this and the next question we're going to talk about give us good reason to actually take both points of this and weigh them against each other. Speaking of the next question, and this was the last question, was, is there an infinity between Aleph naught and Aleph C? Or let me rephrase that question. Is there a set whose cardinality lays strictly between the cardinality of the positive integers and the cardinality of the real numbers? Again, note we're talking about cardinalities here. Certainly there's a set which properly contains the positive integers and is properly contained in the real numbers. For example, the rational numbers is strictly contained in the real numbers and strictly contains the positive integers. But remember, we proved that the rational numbers, in fact, have the same cardinality as z+. So this would not be a strict inequality. It would, in fact, be an equals if you actually looked at it. This question ends up going by the name the continuum hypothesis. And when Hilbert sat down in 1900 to write a list of what he thought were the most important questions to be answered in the 20th century, This was one of the questions Hilbert asked. Is there a set whose cardinality lay strictly between the positive integers and the real numbers? This feels in a lot of ways like a pretty concrete question. It seems like there's only two acceptable answers, namely, yes, there is, or no, there isn't. And I have no reason to believe that Hilbert expected anything different, that he expected the answer would be yes, or the answer would be no, and that it would be interesting to know either way. However, it turns out, unfortunately, that the answer is not yes, and the answer is not no. The answer is that this question is what we call formally undecidable. And so what does formally undecidable mean? It in some sense means that you can provably not answer this question in a meaningful way. But let me elaborate on that a bit. Let's go all the way back to when we were talking about propositional logic at the very beginning of the semester. And so we were talking about statements, like P would be the statement that yes, there is such a set. And then P's negation would be there is not such a set. In other words, going back to our original question, P is just the statement the answer is yes, not P is the statement the answer is no. And one of our fundamental conceits, one of the very first things we talked about at the beginning of the course, was that of a statement and its negation, exactly one of them is always true. But when I say that the continuum hypothesis is formally undecidable, what I'm saying is that one can prove that it is impossible to prove P, and it is impossible to prove not P from the agreed upon axioms. And this is something which you may find fundamentally unsettling. And the reason why this is fundamentally unsettling is that it calls into question the relationship between something being true and something being provable. And we have, through this entire course, tacitly assumed that these two words mean the same thing. That is, that anything true could be proven, possibly with lots of work. We talked about Fermat's last theorem and Wiles's 10-year study in his attic to write this 300-plus page paper to prove Fermat's last theorem, even though it was a fairly simple statement. No one said the proof was easy. But we've implicitly assumed that it was at least doable, that there was a proof of everything true. But here, when you look at this question, these two notions start to slip apart. And the idea of what it means to be true versus what it means to be provable start to have daylight between them. And in fact, you might even start to ask questions like, what does it even mean for something to be true if it's not provable? Or, what does it even mean for such a set to exist if we can't write one down? And these are all very valid questions. These are all questions that mathematicians struggle with. Is there really, in the universe somewhere, a correct answer to this question that somehow we just have the wrong axiom set for? And once someday we find the right axiom to add to the list of axioms of set theory, we'll be able to answer this question. And it will no longer be formally undecidable because we will accept a new axiom about sets. Maybe. This is, in fact, the kind of thing that is studied by logicians. Logicians are mathematicians who look at the structure of logical systems. They look at the axioms, methods of proof, and their consequences, and they consider what the world would look like if our axioms were different. They consider what things are possible to answer within our axiom set, and what things are fundamentally unanswerable. Logicians have proven a great many things, and have been able to answer a lot of questions that have stood unanswered for a long time, by actually showing that the answer to the question was that the question didn't properly have an answer as it was stated. Indeed, one of the biggest theorems in logic is something that's called Gödel's incompleteness theorem. Gödel's incompleteness theorem says that every robust logical system has formally undecidable statements. Where, remember, formally undecidable statements means statements which can neither be proven nor disproven, or neither their statement nor their negation is provable within your axiomatic system. Now, it should be noted, this was rather disappointing to Hardy and Whitehead, who had spent the better part of their lives up until the point where this was discovered, trying to produce an axiom system that contained no formally undecidable statements. And indeed, they had this multi-volume book series that they had already been publishing called Principia Mathematica, which you can look up if you're curious, which was meant to eventually, once it was finished, meet this standard, that this kind of thing didn't happen. That you couldn't accidentally write down a reasonable-looking question and have it turn out that your question, although reasonable-looking, was unanswerable. However, sadly, this is an unescapable problem that will haunt mathematicians for all eternity. You may, by the way, be wondering about this disclaimer, robust. Robust here just means something basically to the effect of your axiom system needs to be complicated enough to know that 1 + 1 = 2. In other words, it needs to be complicated enough to add positive integers, but that's it. As long as it's capable of adding positive integers, your logical system contains formally undecidable statements. And so when I say that this is the kind of thing that haunts mathematicians' minds, the reason why is because what this is really saying is that if you're doing mathematical research, that is, you're taking some unsolved problem and trying to solve it, it is very possible that that unsolved problem is not only unsolved, it is actually unsolvable. And, of course, if you spend all of this time trying to solve a question that actually is unsolvable, you're probably not going to succeed. Now, this leads to all kinds of interesting questions that are pretty natural, like how common are statements that are really undecidable? Are many of the problems that we're currently trying to solve today undecidable? And these questions, in some sense, aren't really possible to answer. We definitely have encountered formally undecidable questions that we thought were natural questions that we were trying to answer. For example, the continuum hypothesis that we discussed earlier. But we know there are others. And we know we could fix the axiom system so that the continuum hypothesis is true or so that it's false, whichever we want. But regardless of how many holes we fix in our logical system, there will always be more holes. Ultimately, this is a very, very, very brief introduction to mathematical logic and the things that lurk beneath the surface, hiding under the difficult questions that we worry about. But if you want to read more of this in a way that I think is fairly lucid and understandable, I recommend the book Gödel, Escher, Bach by Douglas Hofstadter. Now, there are probably lots of copies of this book floating around because I used it for my J-term course in this September, ? So if you're interested, definitely give a look to it. Douglas Hofstadter is not a mathematician. He's actually a philosopher. But among many other topics, he goes through talking about the math behind Gödel's incompleteness theorem, and in fact goes over a very understandable proof of why this statement is true. And in a way, I'll say that once you understand the proof of this, it's maybe reassuring? ? Namely, the way Gödel proves that every system has undecidable statements is to show how to use any particular system to construct an undecidable statement, and the undecidable statement he constructs is not the sort of statement necessarily that you would be interested in. But anyway, if you're interested in thinking more about this philosophical side of things and the logic behind this, this is an excellent read that will keep you entertained for a long time. All of that said, that is the end of the video content for this course. We'll have plenty of time for you to ask questions of me in class before we get to the final, which is sneaking up on us already. But that's all for now. I'll see you around.